Okay, today we're going to talk about using fundamental identities, and we introduced a lot of these back in Chapter 4, so let's get started. So we want you to recognize and write fundamental trig identities. We also want you to use the fundamental trig identities to evaluate trigonometric functions, to simplify trigonometric expressions, and also to rewrite trigonometric expressions. Okay, so when we talk about the fundamental trig identities, if you look on page 374 of your text, you'll be able to see this chart of the fundamental trig identities. Okay, so we recall the reciprocal functions, okay, sine and cosecant, cosine and secant, tangent and cotangent, and these functions are all reciprocals of each other. We also have the quotient identities, so tangent is sine over cosine, cotangent is cosine over sine. We have our Pythagorean identities, our cofunction identities, and our even and odd identities. Now, the ones that we most frequently use are the Pythagorean identities and the quotient identities, and then these reciprocal identities. We don't really use the cofunction ones so often, and every so often we use the even and odd ones as well. So, uses for fundamental trig identities. So what we're doing is we're using given values of trig functions to evaluate other trig functions. And this is kind of similar to what we did in the last chapter later on in the last half of the last chapter. Okay? So given that tangent of x, so tangent of some angle equals square root of 3 over 3, and cosine of that same angle equals negative square root of 3 over 2. We want you to find the other values for the rest of the trig functions. So sine, cosecant, secant, and cotangent. So let's see what this looks like. Well, I know tangent is positive, so I must be in quadrant 1 or 4. And cosine is, quadrant 1 or 3. And cosine is negative, so that must put me in quadrant 3. So all this means I'm in quadrant 3. So when I draw my picture of what this looks like, my theta for my reference angle is going to be in quadrant 3. Now I know that tangent is opposite over adjacent, so this will mean this leg will be square root of 3 and this other one will be 3. Okay, and I know cosine of x is negative square root of 3 over 2. And this kind of might throw you for a loop because you're thinking, oh wow, this leg here is square root of 3, but I know cosine is adjacent over hypotenuse, so right now my brain is really kind of confused because it looks like I want to make this leg square root of 3. So let's just go with the fact that tangent of x is square root of 3 over 3 and find this missing leg and then verify cosine. Now, we know these are negative directions because we're in quadrant 3, but let's use the Pythagorean theorem to find my hypotenuse here. So we have square root of 3 squared plus 3 squared should equal my hypotenuse squared. So that's 3 plus 9 is my hypotenuse squared. So my hypotenuse squared is 12. So h is going to be the square root of 12, which reduces down to 2 radical 3. Okay, so now looking at theta, I can say sine of theta is opposite over hypotenuse. So square root of 3 over over 2 square root of 3. Now, this square root of 3 has a negative value, so my square roots of 3 are going to cancel out, and I'm left with sine of theta equals negative 1/2. Let's do cosine of theta and verify its value. So that's going to be 3 adjacent, which is also a negative direction for us, over 2 square root of 3. Multiplying that by square root of 3 over square root of 3, I get negative 3 radical 3 over 2 times 3. These 3's will cancel out, and I get negative square root of 3 over 2. So I verified cosine, okay, from here. Tangent of theta, we can see is going to be pretty easy. That's just square root of 3 over 3. Now cosecant of theta is hypotenuse, or 2 square root of 3, over opposite. Okay, and opposite has a negative direction, so this is going to end up being a negative 2. Secant of theta is going to be 2 radical 3 over negative 3, right? So negative 2 radical 3 over 3. And then finally, cotangent of theta is adjacent over opposite, and multiplying that by square root of 3 over square root of 3, we get 3 radical 3 over 3, which is just radical 3. And those were both negative, and so they cancel each other out, and cotangent ends up positive. Now let's practice using our fundamental identities to simplify some trig expressions. There's no equal sign here. We can't solve for anything. So we just have to see, well, what can I do to simplify this? Well, I know that cosecant has a reciprocal identity of 1 over sine of theta. Tangent is sine of theta over cosine of theta. And secant of theta is 1 over cosine of theta. Well, doing this allows me to cancel sine, and I'm left with 1 over cosine of theta plus 1 over cosine of theta. That means I have 2 over cosine theta. And about this time, you're going to say, well, how do I know to use these? And you're just going to have to look for things like common denominators. Okay? Look for things that can change form, right? And a lot of this will just be trial and error. Trying something, seeing if it works, learning from your mistakes, going back and trying again. So now let's talk about factoring trig expressions. We can just pretend that these trig expressions are like a different variable. So instead of maybe looking at cosine squared x, think of this as like x squared minus 4 over x minus 2. Now that's not really what it is, but if it pleases your brain to see that as a polynomial versus a trig function, you might find it a little easier to factor. Well, now I can look at this and see, wow, this is difference of 2 squares, right? So I would factor this as x minus 2 times x plus 2. And doing my substitution back, I can say that, wow, this is going to be cosine of x minus 2 times cosine of x plus 2. All of that over cosine of x minus 2. So my cosine of x minus 2's cancel out, and I'm just left with cosine of x plus 2. We also might write this 2 plus cosine x so that we don't have any confusion about what that 2 means for us. It's a vertical shift, not a phase shift. Now let's talk about adding trig expressions. And whenever we add trig expressions, we need to have common denominators. And a lot of times when we get common denominators, we end up having to multiply each fraction by the denominator of the other fraction over itself. So I'm going to multiply this by secant of x plus 1 over secant of x plus 1. And I'm going to multiply this one by secant of x minus 1 over secant of x minus 1. Now my common denominator is going to be secant of x minus 1 times secant of x plus 1. Okay? So I've got some multiplying to do, okay? So this will be secant of x minus 1, and then a minus secant of x plus 1, all of that over my common denominator, which is secant of x minus 1 times secant of x plus 1. Okay? Now I need to distribute that negative, and that gives me secant of x minus 1 minus secant of x minus 1, all over secant of x minus 1 times secant of x plus 1. Well, now my secants cancel on top, and I'm left with a negative 2 over secant of x minus 1 times secant of x plus 1, okay? Now, I'm going to try to remultiply the denominator back out to see if it helps to simplify this even further, because I know that 1 plus tangent squared equals secant squared, right? So secant squared minus 1 would equal tangent squared. So let's see how this multiplies out. I'm going to bring this up here. We'll have 2 over secant squared x minus secant x plus secant x minus 1. These will cancel out, and I'm left with 2 over secant squared x minus 1. Well, I know from my trig identity that 1 plus tangent squared equals secant squared. So secant squared minus 1 equals tangent squared, so I'm left with 2 over tangent squared x. Okay? So when we're looking to simplify things, we want to get them down to the simplest form possible. We want to have one fraction. We want to have the simplest form of that denominator possible. Okay? So a good question to ask yourself is there absolutely anything else I can do to this to simplify it more? Otherwise, you may not get far enough and have it in totally simplest form. Now we're going to use something called trig substitution. Okay? Now trig substitution, this is a technique that you will expand on when you get to calculus and be able to use it more fully. But right now we're trying to teach you the algebra of trig substitution. Okay? So we're going to use a substitute value for x. In this case, we're going to let x equal 2 cosine of theta. Okay? And we're going to limit theta to being in the first quadrant, so between 0 and pi over 2. That keeps everything positive and it keeps us from having to look at extraneous or additional solutions. Okay? So everywhere I see an x, I'm going to put a 2 cosine theta. So my expression will now be 64 minus 16 times 2 cosine theta. And all of that is, and that in parentheses is squared. So when I square this, I get 64 minus, and then it's 16 times 4, which is another 64, and then cosine squared theta. Okay? Now you're saying, well, what else could I do with this? Well, these two terms have a 64 in them, so let's see if I can take a 64 out. So 64 times 1 minus cosine squared theta is what I have now. Well, this should ring a bell with you because 1 and cosine squared are part of a trig identity. So we have 1 plus sine squared equals cosine squared. So sine squared equals cosine squared minus 1. So we have to learn how to recognize our trig identities in various forms. So I can simplify this portion here to just equal sine squared. So I have 64 sine squared theta. Now, 64 is really 8 squared, and sine squared is just sine squared. So when I take the square root of both of these, since I'm limiting everything to the first quadrant, we can only consider positive values of this. So we are actually going to simplify this down to 8 times sine of theta. Now, if I hadn't limited it to the first quadrant, it would be kind of crazy. But we did, so we're good. Another thing we can do is rewrite log expressions, okay? So sometimes we're going to have log expressions that have different things we can do with them, okay? And we have to remember our log functions and how we can combine things with log functions. So let's go ahead and get started with this. So we know that when we have log functions and they have the same base, in this case it's a natural log, then we can, and they're added together, that's like the same as multiplying. But before I get there, I want to simplify things as much as possible because otherwise I'll end up with a real mess on my hands. So simplify, then combine is where we're headed with this. So I look at 1 plus tangent squared of t, and I see that it corresponds to my 1 plus tangent squared equals secant squared. So I can make the substitution that I have natural log of cosine squared t plus natural log of secant squared t, right? Now things are pretty simple, and I'm seeing something that's really nice because I know cosine and secant are reciprocals, and I'm seeing this plus sign in between and thinking, oh wow, I get to multiply them together. So when I do this, I have natural log of cosine squared t times secant squared t, okay? Well, I know this is just really natural log of cosine squared t times 1 over cosine squared t, right? And these two cancel each other out, so I'm left with the natural log of 1, which simplifies down to 0. And oh boy, it's a beautiful thing. Okay, so all that work for just a 0, it's an amazing thing. So we have learned to recognize and write the fundamental trig identities. I've shown you a couple really good examples of how these problems could go. You're going to find that you're going to need to be creative with math, creative with recognizing our fundamental trig identities and seeing, and sometimes you'll think you've got it, and maybe you do, and maybe you don't. So make sure you've got that list of fundamental trig identities handy in your book on page 374. So we're also going to use those trig identities to evaluate trig functions, simplify trig expressions, and rewrite trig expressions. That's it for today.